Okay, this is class assignment 4.4 for Math 153. Some examples that will be similar to homework problems for the same section. So first, evaluate the expression 10 permute 3. Or P 10, 3. Now the formula for permutations is R permutations from n is n factorial over n minus r factorial, where n is the number of objects to be chosen from, and r is the number of objects to be chosen from that amount. And the permutations of r objects from n objects is the number of arrangements that you can make, possible arrangements. So this would be 10 permute 10 minus 3. So 10 factorial over 10 minus 3 factorial is 7 factorial. And what you want to do is take the larger factorial and expand it out until you get to the smaller factorial. So that's 10 times 9 times 8 times 7, so 7 factorial, all over 7 factorial. And those cancel, and you get 720, because 10 times 9 times 8 is 720. Right, next question. Eight permute 4 would be number on the left first, 8 factorial over 8 minus 4 factorial. So 8 factorial over 4 factorial. Expand 8 factorial until you get to 4 factorial. So 8 times 7 times 6 times 5 times 4 factorial, all over 4 factorial. Cancels. And then that will be 8 times 7 times 6 times 5. 1,680. All right, here's a word problem. In a state pick 4 lottery game, a bettor selects 4 numbers between 0 and 9, and any selected number can be used more than once. Winning the top prize requires that the selected numbers match those that are drawn in the same order. Do the calculations for this lottery involve the combinations rule or either of the two permutations rule? Why or why not? If not, what rule does apply? So we are choosing, we have 4 possibilities. First pick, second pick, third pick, and the fourth pick. Now the order doesn't matter, and any number can be used more than once. That means for the first pick we have 10 possibilities. And we multiply that to the number of possibilities for the second pick. Well, any number can be reused. So there's another 10 possibilities. and then another 10 possibilities, and another 10 possibilities. So the total number of possible picks for this lottery game is 10 to the fourth. This is an example of the multiplication rule. And so we would go with the combination rule. Let's see. The combination and permutation rules do not apply because repetition is allowed and numbers are selected with replacement. So it's not like we're choosing, given 10 digits, choose 4 of them, and with order mattering or order not mattering. That would be a permutation or a combinations problem. And we're not allowing making a pick of 4, but then not replacing one. That would be, not replacing a digit after you've used it. That would be an example of factorial. So here, this is an example of a multiplication rule. So we want to go with, it looks like A. Problem 4. A presidential candidate plans to begin her campaign by visiting the capitals in 4 of 45 states. What is the probability that she selects the route of 4 specific capitals? So the route of 4 specific capitals implies that order matters. Okay. So think permutation. Now we have 45 possibilities, 45 possible capitals. So n is equal to 45. And 4 capitals selected. So R is equal to 5. So this specific capitals means, so say she wants to visit Boise, and then Sacramento, and then Carson City, and then Juneau. So say specific route. Then the route Carson City, Boise, Juneau, Sacramento would be different. From the specific route. The specific route of Boise, Sacramento, Carson City, Juneau. So we need permutations. To figure out the sample space. So in permute R would be the number of permutations from 45 possibilities into groups of 4. And that is going to be 45 factorial over 45 minus 4 factorial, which is 45 factorial over 41 factorial, which is 45 times 44 times 43 times 42 times 41 factorial over 41 factorial. Whoops. So the 41 factorials cancel. And then we have, let's multiply what we have left, 45 times 44. 3,575,880. So probability of selecting a specific route, 1 over 3,575,880. All right. Question 15, but really question 5. At a private school, each first-year student is sorted into one of 4 houses. So there's 4 possibilities. If 6 students are randomly selected from 15 available students, what is the probability that they are the 6 youngest students? So here, order doesn't matter because all students are equal. So really, we are looking at 15 available students. Means n is equal to 15. And 6 students are randomly selected. 6 students selected implies R is 6. So since the order does not matter, that means we need combinations. Or in combinations, or R combinations from n objects, students in this case. The formula is n factorial over n minus r factorial times r factorial. So 15 possibilities, choose 6. Would be 15 factorial over 15 minus 6 factorial times 6 factorial. 15 minus 6 gets us to 9. And then we can break the 15 factorial down into 15 times 14 times 13 times 12 times 11 times 10 times 9 factorial, and then times 6 factorial. So the 9 factorials cancel. And then we have 15 times 14 times 13 times 12 times 11 times 10 over 6 times 5 times 4 times 3 times 2 times 1, but we don't need the times 1. So you could start canceling out like factors if you'd like. Well, I see that 3 and 5 cancel out with 15, so that's reasonable. Also 6 and 2 cancel out with 12. So we have 14 times 13 times 11 times 10. So 14 times 13 times 11 times 10 is 20,020. So the probability that they are the 6 youngest would be well, there's only, assuming that none of them are the same age, exactly the same age, then there's only one possible grouping of the youngest. So we have 1 out of 20,020. Oops. Let's see. Oh, I missed this 4 here. So this 4 doesn't really divide. You know, we could cancel out a 2 here. But it would be easier to divide the 20,020 by 4. So let's do that. 20,020 divided by 4. 5,005. So 1 over 5,005. All right, next question. Okay, problem 6. Winning the jackpot in a particular lottery requires that you select the correct 4 numbers between 1 and 50. In a separate drawing, you must also select the correct single number between 1 and 17. So we have That means that we want to take the number of combinations of 4 numbers from 50 possibilities. Because it doesn't state that the order matters, so we want combinations. And we have to choose, we have to select 4 things out of 50 possibilities, so that's a combinations problem. But then the sample space is also going to include one single possibility between 1 and 17, so times 17. And that will be the sample space size. This hash symbol means size. I'll just write sample space size. So, from 50 things, how do you choose 4? That's 50 factorial over 50 minus 4 factorial times 4 factorial. 50 factorial is 50 times 49 times 48 times 47 times 46 factorial. And I know to do that because 50 minus 4 is 46. So we have a 46 factorial down in the denominator times 4 factorial. So the 46 factorials cancel. And we have the calculator. 50 times 49 times 48 times 47. And then you write that down. Four factorial is 4 times 3 times 2 times 1, so 24. So 24 here. So then divide the 5,527,200 by 24 to get 230,300. So the sample space size is equal to the number of combinations of 4 numbers from 50 times 17 other possibilities. So that's 17 times 230,300. Which is 3,915,100. So the probability of winning the lottery here is 1 over 3,915,100. Right, next. A classic counting problem is to determine the number of different ways that the letters of millennium can be arranged. So MILLENNIUM. So note that we have repeated M and M. So one of the things is repeated twice. Notice also that the letter I is repeated twice. So we have another repetition, and the letter L is repeated twice. Let me use a red here. So in 3, one object is repeated twice. And even it looks like E and U are the only unique letters, the only letters that show up exactly once. So N and N is repeated twice. But in total, write that up here, is the number of letters in the entire word. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the permutation counting rule for repeated objects is, if you recall, n factorial over n1 factorial times n2 factorial times the factorial of all the objects that are repeated more than once. So for us, the number of permutations of letters that spell millennium is equal to n factorial 10 factorial over 2 factorial times 2 factorial times 2 factorial times 2 factorial. Which is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And then 2 factorial is just 2, so 2 times 2 times 2 times 2. So the 2's cancel, and 2 times 2 is 4, so that'll cancel with the 4. And this factor of 2 could cancel with the factor of 2 and 6 and leave a 3. So then that's 10 times 9 times 8 times 7 times 3 times 5 times 3, or 226,800 ways to arrange the letters that make up the word millennium. All right, let's consider problem 8. You want to obtain cash by using an ATM, but it's dark and you can't see your card when you insert it. The card must be inserted with the front side up and the printing configured so that the beginning of your name enters first. So, what is the probability of selecting a random position and inserting the card with the result that the card is inserted correctly? Well, let's see. It must be inserted front side up. So let's make a random card. So front side up. So up or down. And then presumably you're not going to try to stick it in lengthwise. You can feel with your fingers to stick it in from here or from here. So let's say that the name starts here. Okay, so then you have name side, or we'll say name first, name last. All right. So only one of these would work. The sample space of possible ways of so the number of ways to insert the card would include, is it up or down? So that's 2. And then is it name first, last name, or name last? Well, there's 2 possibilities there. So we get 4. So the probability is 1/4. You could even draw out the sample space. So you put it in front up and name first, front up, name last, front down, and name first, or front down, name last, all backwards. So that size of that set is 4. And the only one that is correct, so the probability of correct insertion is front up, name first. So 1 out of 4. What what is the probability of randomly selecting the card's position and finding that it is incorrectly inserted on the first attempt, but is correctly inserted on the second attempt? So assume that the same position used for the first attempt could also be used for the second attempt. Well, assuming that the same position, assuming this statement, that means that they're independent events. So if you get it wrong on the first attempt, so the probability of, what is the probability of a not a correct insertion? It's 1 minus the probability of a correct insertion, because they're complementary events. Either you insert the card correctly or you don't. So that's 1 minus 1/4, which is 3/4. So the probability first attempt incorrect would be 3/4. Well, let me write out what we're trying to find the probability of. So the probability of first incorrect and second correct is, so first incorrect, you multiply the probabilities together because they're independent. So 3/4 and second correct, probability of the second being correct is 1/4. So we get 3/16. How many random selections are required to be absolutely sure that the card works because it is inserted correctly? Well, let's see. If they're random selections, it is possible to get it wrong every time. For all, emphasis on all random selections, it is possible to always insert the card incorrectly. So this would be a trick question. Okay, problem 9. In the game of blackjack played with one deck, a player is initially dealt 2 different cards from the 52 different cards in the deck. So initially dealt 2 cards from 52. So that means all the combinations of 2 cards from 52. So 52 factorial over 52 minus 2 factorial times 2 factorial. So 52 factorial over 50 factorial times 2 factorial is 52 times 51 times 50 factorial over 50 factorial times 2. And the 50 factorials cancel, and we get 52 times 51 divided by 2, 1,326. A winning blackjack hand is won by getting one of 4 aces, so or one of 16 other cards worth 10. So number of winning hands is equal to possible aces, which would be 4, times possible 10-point cards, which would be 16. So the number of possible winning hands is 4 times 16, or 64. So the probability of a winning hand would be 64 possibilities, possible winning hands out of 1,326 possible 2 cards dealt. So 64 divided by 1326, we're going to need that in fraction form. So 2 will divide 1326, and 663. So cancel out factors of 2, left with 32 over 663. So the probability is 32 divided by 663. So the percentage of winning hands would be, well, let's see, 32 divided by 663, 0.0, so it looks like 4, we have 0.04826. So bump this decimal over to here, and we get 4.83. This 6 will round the 2 to 3. 4.83%. Alright. You can try the traveling salesman. Yeah. Alright. And that's it for the class assignment.